And you will never use these terms again in your life as an electrical engineer. For two reasons. First of all, most of you probably won't go into really hardcore astronaut design when you get out of here. The second thing is that you're never orbiting something in the abstract. You're orbiting specific things. And when you orbit specific things, it turns out that you use a different word for each specific thing that you're orbiting. So let's come class to orbit the Earth, right? That's where we live. This is where most satellite communication takes place. And in that case, this is called the perigee. And the Apple abscess is called the apogee. You got G instead of Apple. Okay, now this is going to be a technology. It always goes badly when Professor Durkin tries to do something technical. I'm going to attempt in this room for the first time to use the document camera here. I don't even know if I can do this. The light. And power. That was always good. Okay, let's see if we can. Oh, this is excellent. Thanks, Sean. Thank you. Good job. Oh, look at this. All framed and everything. This is taken straight out of Wikipedia. Shame. So it turns out that everything that you orbit that's different has a different name. You know, this is one of the rare instances when the engineering profession or the physics profession starts to resemble the legal profession. You know, where you take your profession and you shroud it in some dense, pointless jargon to keep the outsiders out. Look at this. Everything that you orbit, if you orbit the moon, well, okay, let's finish the glory. If you orbit the sun, the periapsis is actually the perihelion, and the abscess is the aphelion. If you orbit something like the moon, you notice that there's even like competing terms. Oh, is it the periselene, pericythian, perilune, apocylene, apoloon. Jupiter, perizine, perijove, apozine, apojove. Two different competing terms. My favorite is this one, the black hole. We've never sent anything in orbit around a black hole. And yet there are three competing conventions. Perimelasma, perimorpha, or perinigricon versus apomelasma, apomorpha, or apathy. I'm going to science fiction writers for that one. So be careful. You will probably hear me make this mistake once or twice during the course of this class at least. Well, we'll be orbiting something other than the Earth, and I'll accidentally call it an apogee or a perigee. Aerospace engineers make that mistake too. It's fine. You're too kind to say no. Okay, that's fine. So anyway, that's why I want to use the document camera. It's about as multimedia as we get in this class. Okay. Let's do an example using elliptical orbits. Here's the problem. We're not the Earth. It pains me to say this, but I once had to do in this class, I was saying, well, how do they get spacecraft in space? And I had to pause for a second, and I had to say, rockets. Does everybody know that? You need a rocket to get into space. We'll talk a little bit more about rockets for the next lecture. But you launch a satellite into space with a rocket. And all satellites start off in lower orbit at some point in their trajectory. They're launched into space. They're beyond most of our atmosphere at that point. You know, the atmosphere magically stop at some altitude. But it tapers off gradually. You know, it gets at 35,000 feet. You already get pressure on the cabin in your airplane. But it still tapers off quite a ways away. If you still get residual drag at hundreds of kilometers above the surface of the Earth. But at some point, you get high enough where the drag is negligible and you can make lots of stable orbits around the planet without having to re-energize the orbit. Or propel it as such. And then, if your final destination is one of these higher orbits, at some point you've got to engage another rocket to propel your spacecraft to a higher Earth orbit. So, this problem, we are going to start off at R1, a circular Earth orbit of 1,000 kilometers. And we want to wind up in a medium Earth orbit of R2 of about 20,200 kilometers, which coincidentally, or not so coincidentally, since the instructor engineered the problem, is the altitude of a GPS satellite. So, how do we get there? We're orbiting here. We got to jump into this orbit. Well, there's a lot of different ways to do it. Nowadays, people talk about things like ion drive. We actually have some launches that where a small, low-powered ion drive provides very little force, but can do so continuously for a very long amount of time with relatively little payload weight, little fuel weight. In that case, what happens is that you slowly, over the course of days, spiral up until you get into medium Earth orbit, in which case this ion drive shuts off and engages. And voila, there you are, medium Earth orbit for the rest of the satellite's useful time. There's another way to do it, and it burns more fuel. But what you can do is at a particular point, you fire your thrusters. And you just not enough to really move appreciably. It's almost like it's 8 to take a energy. And that launches you into a higher energy orbit. And you start up at this point, but you've got more kinetic energy at this point, so you're going to wind up being in an elliptical orbit. And if you time the amount of energy right, you can make it so that your apogee switches the desired orbit that you want to get into. So your energy is in your original circular low Earth orbit, and your apogee is at your final negative Earth orbit. And when you get up here, you got to give yourself another rocket thrust in the backwards direction to kind of propel you forward, thrust you forward, so that you circularize the orbit. You bring your velocity up so that it matches the velocity of the equation that we put on the board 30 minutes ago for a circular Earth orbit. You're not going to be short of that velocity, you just stay in elliptical orbit. So with two controlled burns, you can do a very efficient transfer that takes only half a period of the elliptical orbit. Now, this has a special name. This is orbital transfer. Aerospace engineers know this as a Corbin transfer. So my question to you now is, what's the period? How long does it take to get from this point to this point if I was doing a Corbin transfer for a GPS satellite? So let's go ahead and figure it out. First of all, I did it again. This is R1. This is a radius. I need to add 6380 kilometers to get a radius. 1,000 kilometers is the altitude of the lower orbit. And likewise, to get a radius, I'm going to take an altitude. I got to add 380 kilometers. The word of the problem was that for people on the board is that altitude is not radii. So I got my two radii. I'm 7,000 kilometers here. I'm going up to 26,000, 26,500 up to medium Earth orbit. How long does that take? How long does that take? What's the eccentricity of the orbit? So, we know that perigee is equal to A, my semi-minor major axis, times 1 minus E. And the apogee is equal to A times 1 plus E. Why is that true? Well, remember, the Earth is going to be at a focus. The centroid is at a focus. The R value, R1, of the perigee plus R of the apogee for this orbit, if I drew it correctly, they should be equal to, the sum of those is twice the semi-major axis. We know this is the center, and E times A. So from this point to the center is A. I have to go another EA to get to the focus, which is the center of the Earth. So 1 plus E times 1A is my apogee, and 1 minus E therefore must be my perigee. And let's see, so if I divide these for the ratio of these, 1 minus E over 1 plus E should be equal to 7,380 kilometers for the perigee divided by 26,580 kilometers for the apogee. Solving for E gives me an eccentricity of 0.56, fairly eccentric. That's eccentric, certainly not circular. Now, what's the period? Let's use Kepler's second law. That says T squared is equal to 4 pi squared A cubed over Kepler's constant, GMT for the system. What is A going to be? Well, A, my semi-major axis, is really just the average of perigee plus apogee. So I average these two quantities. I solve for T. What I get, T is equal to 11,000 seconds or 3 hours and 3 minutes. That's the amount of time it will take to do a Hohmann transfer for the GPS satellite. I should say, this is TR2. So remember, you only got to go through half of the orbital period to get to the actual orbital period is 22,000 seconds over geometry. And then what is the final orbital speed? What is the final orbital speed? Well, that we calculated earlier, right? A theta is equal to the square root GMT divided by your final radius. The final radius is 26,580. 6 times 10 to the 24 kilograms. Constant 6.67 times 10 to the negative 11. We get 3.8 kilometers per second. So you can see, these spacecraft, relative to our observation of the Earth, are actually moving very quickly. They may only be drifting across the sky, but they're moving in thousands of meters per second in order to maintain a stable orbit. It's one of the reasons why we have to launch with such powerful rockets, right? Giant chemical rockets to get these things into space. Because we have to add all that kinetic energy. I mean, relative to the surface of the Earth, we're only moving at a few hundred meters per second with regards to the Earth's rotation. And so we've got to get up to, at least with this lower orbit, I've got to get into at least 7 kilometers per second, in addition to the potential energy that it takes to get there. So that's a tremendous amount of energy. And I think I'll do one more fun example of an elliptical orbit. We'll do a deep space mission and figure out how long it takes an actual satellite to get to a planet using gravitational slingshots. So So let's go ahead and start off with that example. Before that, do we have any questions about previous material? Don't be bashful. Do you have a question? No, nothing. Perfect understanding of it. Okay. No problem. Now, the trick to get satellite communications to work, of course, is to find these stable orbits that you can put in spacecraft. The spacecraft have to be in these stable orbits because this isn't Star Wars. There's not enough energy that you can pour into space to have a spacecraft flying around wherever it wants to go, like the Millennium Falcon or something. We had a reporter from a Canadian news station that was interviewing me. It was about the plane crash, disappearance of the Malaysian plane, and then went over the Indian Ocean. He said, well, we're getting these sporadic reports of surveying satellites. Why can't we just fly all the satellites over there and kind of listen, look down, look at what's going on there? And I said, well, you can't really do that because there's a gas station in space for starters. There's fuel that we need in space we got to take up there. So it would become relatively expensive. We have to take a little bit of fuel up there to perform station keeping exercises. So we're going to learn about a little later today and next week is there are perturbations and things that we have to overcome so that we stay in those idealized orbits. And so we may have to fire the rockets for a little bit once a week to do minor course corrections. That alone, those tiny little bursts and corrections is usually what limits the usable lifetime of a spacecraft in outer space. So the satellite lasts 10 or 15 years, usually because it can only take 10 or 15 years of station keeping fuel in outer space. And so that's kind of where we're going. We'll cover more of that stuff towards the end of astrodynamics. We'll get into spacecraft subsystems. We'll talk about the power systems and the propulsion and attitude control and our subsystems and some of the high-level pieces that we have to put together to get a spacecraft functioning. So here, let's go ahead and do a fun thing. Okay. Now, we talked about orbital transfers last time. Going from like a lower orbit to a medium or a higher orbit. And they're usually about firing thrusters. Sometimes you can fire a thruster for a little bit and transfer it using a home transfer. Sometimes you just blast off. You're willing to pay for the fuel. You can just blast off and kind of accelerate until you're in a high enough orbital altitude and circularized with your thrusters. You can do an ionic drive. You can do a very slow burn and wind your way out to the circular orbit that you need over the course of many days. Now, when you were talking about interplanetary missions, most of those options aren't available to you. Because even to do things like a Hohmann transfer or a continuous burn is prohibitively expensive in terms of the amount of energy and fuel you need to take into outer space. We have enough to get out of Earth's orbit to hit escape velocity, and then after that, you're usually wet. You have very little left. So you have to think about a way. How do you get to we send spacecraft to all the planets? So how do we do that? What's the trick? Well, in this class, we study only two-body problems, and everything else is sort of this non-ideal correction factor or disturbance that you have to deal with. However, the real solar system is a multi-body problem, right? And there's a trick that you can use when you have three bodies to operate against, and it's called a gravitational slingshot. So, let's say here's the sun, here's a planet. The planet is, of course, itself orbiting around the sun in a roughly circular orbit. And let's say that I have a spacecraft. My spacecraft. You draw the launch with two solar panels. That's my scanner. Symbol for a satellite in this class. And the spacecraft is coming in. What happens when it gets to the planet? Well, keep in mind the spacecraft is not orbiting around the planet. It's orbiting around the sun at this point. It's going to accelerate as it gets close to the planet. But it will never orbit the planet unless you do something to the spacecraft, like fire the thrusters and insert yourself into the orbit. Because it already has enough potential energy to kinetic plus potential energy to escape the gravitational pull of that planet. So if it comes in, it's not magically going to just start circling around the planet. It will bend in the gravitational field, but it will not insert itself in orbit. And if you line up to bend properly, let's say the planet is going this way, as this spacecraft comes in, if you let it kind of come around the backside, it will bend, and when it leaves, it will actually have more kinetic energy than when it started with. Now, are you violating the conservation of energy there? No, what you're physically doing is borrowing a little bit of the momentum of the planet itself, effectively. So, this planet is moving around the sun. if it was just stationary in space, if this was a fixed system, somehow you would hammer them into the fabric of space and time, nothing would happen. You would basically just change the direction of the orbit, but it would be in the same energy orbit effectively. However, because this planet is moving, it spends more time falling towards the planet than it does flying away. So you actually gain some momentum when you do that. And if you are very careful with your calculations, taking during the exit, you could be in a completely different higher energy orbit. And so the trick is to take one or more of these gravitational slingshots, piece them together, and hope that the endpoint is the planet that you want to visit, or the place in the solar system that you want to visit. So you often hear about these space missions where, the planets are lined up, and you go, yeah, they're all in a row. Right? No, it's just that you have to do all these crazy calculations when you have this complicated multi-body system, and there are certain windows in which you can actually get a spacecraft to bounce around to all of these different planets. And that's actually what kind of happened in the 70s when they launched Voyager 2, I think, the one that went to all the outer planets. The planets were lined up so that you could actually slingshot from one to the next. And then actually out of the solar system is the last stop. So let's go ahead and work an example. Let's just see if after one full lecture of satellite communications, we have enough static to plan a deep space mission using gravitational slingshots. So here's the problem statement that we're going to work on. Ripped from the headlines. So at some point in next year, 2016, a spacecraft that NASA launched in 2011, the Juno spacecraft, will reach Jupiter. It's a new science mission to Jupiter. It's called the Juno mission. The launch date was August 2011. If I can draw a map of the solar system, here's the sun. Here's the Earth orbit around the sun. And then at a higher orbit is Jupiter. Okay. So here's the plan. The spacecraft, in August 2011, is going to launch. It's going to get escape velocity of Earth very quickly. They're going to burn the rocket to get it out of Earth. And it's shut it into a sun orbit. There's not going to be enough rocket fuel to get an elliptical orbit that will only transfer to Jupiter because the rocket would be bigger than, a dozen Saturn V or something like that. It would be prohibitively expensive and risky mission. So instead, it'll be a slightly higher orbit, an elliptical orbit, that makes one pass around the sun. And then, unlike a lot of other space missions where you slingshot around Mars or Venus or something like that, this spacecraft is actually going to slingshot off of Earth, the place that it started from, right? Its planet of origin, which will put it in a higher elliptical orbit, and then it'll reach Jupiter. So we have 1, 2 to slingshot. So basically, one full period of this orbit and a half period of this particular orbit. Well, let me give you a couple pieces of salient information. Of course, we're going to use Newton's gravitational constant. This is Newton meter squared per kilogram squared. The mass of the sun, you thought the Earth was massive, check this out. It's about 2 times 10 to the 30 kilograms. When it gets that high, it starts to get ridiculous, like, it's like with 10 to the 30. It's like dimensional gig. That's ridiculous. We don't understand numbers that big. Okay. Not quite cute. 3.25 times 10 to the 11th meters is, I'll put that number up there for a second, or Jupiter, that's the aphelion of this orbit. And in this problem statement, which is ripped from an examination, and the radius of Earth, the mean radius from the sun to its roughly circular orbit, is 1.52 times 10 to the 11 meters. Jupiter's about, it's a little over 4 to 5 times the distance from the sun that the Earth is. So a tremendous amount of gravitational potential energy from the sun that you have to overcome to move up there. And so we put it in this elliptical orbit, and I've gone ahead and given you what the aphelion is. Remember, we call it's not the apogee or the apoapsis. The apoapsis around the sun is the aphelion. The aphelion I've calculated for you. I could probably not give that to you in an exam, and you would still be able to calculate it. Okay, so for some reason, some students struggle with this concept of this particular orbit I found in the past. It's a brain teaser, but it's really not that hard. Okay. How many years does it take the Earth to revolve around the sun? 1, right? Okay. So you are launching this satellite into a higher orbit than that. So you expect to get a number greater than 1. whatever greater than one number you get, it had better be an integer, because the Earth needs to be at the same location that you left it in order to slingshot. You can't slingshot it around like a ghost planet, right? And so, however, the higher this orbit is, this initial orbit, the more energy you have to expend to put it in there. So, what is the smallest integer greater than 1 that would make sense to be the period for that first orbit? Don't all tell me at once. The number is 2. The number is 2. This orbital period is 2 years. And let's see, if you average these two together, that would give you the semi-major axis. You actually put that into Kepler's second law and third law and calculate the actual period of that one, and it would be 2.0. Does everybody understand that reasoning? How we practicing just a combination of common sense and astrodynamics arrived at a period of 2 for that orbit. Yeah, okay. I don't know, there have been some times I had some classes with that.